We are Team 116 of the Electrical and Computer Engineering program here at PKI. This video is going to demonstrate that our project meets its success criteria for our capstone project, which we have named Abraxas. My name is Connor Yax and I served as the systems engineer on this project. I'm an electrical engineering major with a minor in physics.
My name is Nate Tyler. I served as the project's software engineer, and my major is computer engineering.
My name is Parameli Mangamana. I'm hardware engineer for this project in the computer engineering.
The case study for this project is that of free-range chicken farmers. Their flocks get constantly attacked by predatory birds, most commonly bald eagles. These birds are protected by federal law, so there's not much the farmers can do against them. Currently, the only solution that works effectively is to use pyrotechnic pistol that launches noise-making projectiles at the incoming birds. This does deter the birds, but requires extensive manual labor as the launchers must be operated by humans moving around the farm. The goal of our project was to automate this process by using machine vision and a motor-controlled turret to move the pistol. From this problem statement, we derived this objective tree. The main goal of our project is to detect and deter raptors. To do this, our solution needs to be able to identify raptors, repel them with a projectile, and do all of this in a set response window. In order to detect an incoming predatory bird, we set forth that our system would need to be able to detect an object moving below a maximum velocity at a set maximum distance and a set minimum size. To repel the raptor with a projectile, the system would need to fire in the general direction of the target, but would not have to be perfectly accurate. To conform to the federal law, the device could also not harm the raptors. The separate components to make up the system's response time are the time it takes for the system to identify the target, compute a target position, position the launcher, and fire the projectile. This is our solution, Abraxas. Abraxas is a vision-based automated detection and repellent system. It uses motion-based camera vision to detect incoming threats. It has 2 electric motors to position a pyrotechnic projectile launcher. The launcher is triggered by an electric solenoid. The entire system is controlled by an STM32H microprocessor that is on a custom-built PCB board. Here is a block diagram of Abraxas. The vision system consists of a camera array connected to a Jetson Nano. The Jetson Nano processes this camera data from the array and calculates an X-Y tracking coordinate. It then sends this to the fire control board's microprocessor via a USB to UART connection. The STM32 microprocessor processes the tracked coordinates, and once enough coordinates have been received, it computes a target position. It then sends pulse width modulated signals to 2 different motor controllers. These 2 controllers control the rotation motor and the elevation motor. Both motor controllers receive control signals from the microprocessor, which they then translate into voltage control signals to send to their respective motors. Once the motors have reached the target position, the STM32 sends a launch signal to the launcher relay that then switches on AC voltage to the launcher solenoid, launching the projectile. This is a recording of our full integration test to make sure the system is working. We use some balloons to generate a target from the vision system. Here is a slowed down version of that clip with some tracking on the projectile to make it easier to see. Our first project-specific success criteria is that the system will respond in 4 seconds once a target has been detected. To test this, we fed the worst possible target into the system and then measured the time it takes the system to reach that target. As you can see from the following video, we are easily under this threshold and meet this success criteria. Our second project-specific success criteria is that the system will be able to detect an object of at least 4 square feet moving at under 30 miles per hour at the system's maximum detection distance. Because getting a flying object that big that can move that fast would be costly, we use something else. We measured the amount of pixels a 4 square foot object took up at our maximum distance, and then moved a smaller drone closer to the camera until it was just under the pixel count of the 4 square foot object. We measured this distance at just under 40 feet, so we rounded it up to 40 feet. We proved our system could see this drone by flying it back and forth at 40 feet away from the camera. The system shows that it is detecting an object by drawing a green border around it. The max speed of this drone is only 20 miles per hour, but if we treated it like a larger object further out, we could calculate how fast it would be moving at this further distance. We then made sure that our system could detect the drone moving at its max speed. Here's a diagram of the setup we made along with the math behind our results. Next, you will see a slowed down video of the system detecting the drone moving at its maximum speed. The red circle is the coordinate that the vision system is sending to the fire control board. This video has been slowed down from its original speed to make viewing easier. Our third project-specific success criteria is that the system will run on a standard North American outlet that supplies 120 volts AC and 20 amps of current at 60 Hertz. Our test for this PSSC is to run the same worst-case target through the system that we did before PSSC 1 while measuring the current draw. If the current is under 20 amps, we meet this PSSC. As you can see from the following video where we ran this test, we are easily under this threshold. Our fourth project-specific success criteria is that the camera system will have an effective operational zone of 200 feet from the camera with a field of view, or FOV, of 160 degrees horizontal and 70 degrees vertical. We tested this PSSC in parts. First, the 200 feet part was already confirmed in our first PSSC test. To measure the horizontal FOV, we made chalk lines of the required angle on the ground, then placed poles on these lines. The setup can be seen in these photos along with a screenshot showing the vision system clearly showing both poles in the FOV of the camera. To measure the vertical FOV, we calculated what distance we would need to place a yardstick at in order to see the top clearly. We then took this photo where we placed it at the computed distance of 13.1 inches. Our fifth and final project-specific success criteria is that the two different boards would be connected with a USB 2.0 standard connection. To make sure we were meeting the USB 2.0 standard, we are testing to see if we meet spec 7.1.7.1 or the voltage signal level specification. The difference between the two data lines for logical 1 must be above 200 millivolts, while for logical 0, it must be less than 200 millivolts. These images prove that we meet this PSSC. Team 116 would like to give special thanks to the University of Nebraska Lincoln Physics Department for their help machining several parts for us.